In this video, we will learn two important definitions. One is angular displacement and the other is angular speed, and how angular speed is related to the linear speed. Let's assume that there's a particle here which is moving at a constant speed v around a circle. So the speed of this particle is constant, and let's assume that for the particle to move from point A to point B, it has covered distance AB, which is the arc of the circle, in time delta t. So v, the linear speed v, is AB by delta t. Let's call this equation 1. The definition of angular displacement. Angular displacement is the change in the angle from a particular reference point. In our case, let's take A as a reference point. So as the particle moves from A to B, it moves through an angle delta theta. So delta theta is our angular displacement. So I repeat, angular displacement is the change in the angle from a particular reference point. Delta theta is our angular displacement. Now, if we were to assume that this particle is moving at a constant speed v, then it is also moving at constant angular speed. The angular speed is the rate of change in angular displacement. So angular speed omega is equal to the rate of change of angular displacement. Now our angular displacement in this case is delta theta, which is this, as a particle moves from A to B, and this distance we know has been covered in time delta t seconds. Let's call this equation 2. We know by definition of radian that delta theta is equal to arc AB divided by the radius of the circle. Let's call this equation 3, and let us substitute the value of delta theta here, so that our equation 2 becomes omega is equal to AB divided by r delta t. Now if we look closely at equation 1, you will notice that linear speed v is AB by delta t. This is our linear speed. So substituting the value of v, because v is equal to AB by delta t, we get the relationship between the linear speed and the angular speed. So this is the relationship. If we rearrange the equation, we can say that v is equal to omega r. So the linear speed of a particle moving in a circle is dependent on two factors. It's dependent on the angular speed, as well as it's dependent on the radius of the circular path. So if we had an object at a smaller radius here, it would cover lesser distance from, let us say, point A dash to B dash. So the distance covered is less in the same time, so its linear speed is going to be less, though its angular speed is same, because it has covered the same angle delta theta in delta t. So this brings us to a very important relationship between linear speed and the radius of the circular path. As the radius of the path followed by an object increases, the linear velocity also increases provided omega is constant. Now let's move on from here to define period. What is period? Period t of the rotational motion is the time taken for the particle to complete one revolution. So in one revolution, this is the time taken for the particle to complete the full circle. So for this particular particle, the angular speed is equal to the angular displacement, which is 2 pi, because when the particle moves full circle, it covers 360 degrees or 2 pi radians, and t is the time taken. So omega is 2 pi by t. We know frequency is the reciprocal of time period t. Frequency is 1 by t. So if we substitute 1 by t here, we get omega is equal to 2 pi f. So this is another important relationship that you should remember. So to recap, this is a very important equation. V is equal to omega r relates how the linear speed is related to the angular speed and the radius of the circle. And omega is equal to 2 pi f is another important equation that you should remember. Thanks for watching.